last time we were doing Dijkstra's algorithm. I was originally planning to analyze that algorithm first thing in this class, but then I sort of started to feel like we might just get bogged down in the details. And actually, at this early point in the course, I want to keep things kind of moving. So it's like not a hard algorithm to analyze. It's all written down in the notes, but I would like to rather than analyzing that, I want to just kind of move on to a new topic here. Actually, before I do that, maybe a few more comments about the shortest path problem. So, so last time I mentioned when we introduced Dijkstra's algorithm that it works for non-negative length functions. So the length function maps every arc, right, to a non-negative real number, which is like non-negative length functions are pretty natural for a shortest path problem, right? I mean, if you actually have a network of some sort, if you want to find the shortest path, like usually you won't have, from here to somewhere else, usually won't have a negative distance. But in principle, you might be interested about, in solving this problem for other length functions. So there's more generally, there are algorithms well, let's say efficient algorithms. Of course, there's always an algorithm to find the shortest path. Just try all the paths. But we care about efficient algorithms when the length function is conservative. So I'll tell you what that means. So conservative just means that there are no negative cycles. Okay, so for example, when I say a negative cycle, I don't mean a cycle where so a cycle is just like a sequence of vertices and arcs where you start somewhere, it points to the next one, it points to the next one, et cetera, in a cycle, right? When I say negative cycle, I mean a cycle where the total, if you sum up the lengths, you get a negative number. So a negative cycle would be something like, I don't know, if I've got -3 on that arc, 2 on that arc, -1 here, and 0 on that arc. Then if you go around and you sum up all the lengths, you get like -2, right? Okay. So if there are no negative cycles, so the Dijkstra's algorithm isn't going to work. There's a place, if you go through the analysis of the algorithm, there's one spot where it's just not going to work. The analysis kind of requires that, if you take a path from here to here, and you take basically that as you take a longer path, the lengths increase. But if you have negative arcs somewhere, you might take a longer path and it actually has lower length. But yeah, if it's conservative, there are algorithms. And more generally, if you just look at all length functions, there's pretty much no chance. So for general length functions with no restrictions, I'll just say the problem is hard. Put that in quotes, but hopefully by the end of this class, we'll have like a better sense of what I mean by hard. Okay. And actually, by the way, on your assignments, like so on question 7, assignment 2, you'll actually prove that if you have conservative length functions, there's a polynomial time algorithm by reducing it to linear programming, which is something we'll talk about soon. And actually, on question 6 on assignment 1, you're going to demonstrate that if you have general length functions with no restrictions, the problem's hard. Okay, so these things are going to come up in your assignments. Okay. So in this lecture, what I want to kind of focus on is something that's actually quite philosophical and theoretical. So here's I think a natural question, especially when we're talking about problems being hard or tractable, efficient algorithms and stuff like that. Here's a question: what makes some problems harder than others? This is a very, very theoretical question. And actually, I'm not going to be able to answer this question in this course. In fact, if any of you are able to answer this question, then if you submit the solution, you'll get $1 million from the Clay Math Institute. So this is really a $1 million question. Literally, they will literally write you a check if your solution's correct, right? Okay, so it's extremely hard to understand genuinely, like rigorously, what makes one problem strictly harder than another. I mean, it's extremely difficult question. So yeah, we won't be answering that in this course, unfortunately. But we're going to build up tools to sort of compare the hardness of different problems, and also to show that some problems are tractable, meaning that they can be solved efficiently. So we're going to try to solve things efficiently, and when we can't, we're going to kind of be able to compare the hardness of some problems to other problems, basically. Okay, so basically in this course, any algorithm, so an algorithm in this course is going to be thought to be efficient if it runs in polynomial time. So this is a standard kind of idea. So an algorithm. So in this course, we're going to say it's efficient, although of course, in general, you could be interested in other measures of efficiency. But we'll say it's efficient if the running time is big O n to the k for some fixed, so k is just a constant, where n is the size of the input. There's always going to be some kind of maybe a question of what is the input and how do you represent inputs to these problems, right? Like, I mean, okay, last time we were looking at like a sorting algorithm. You have n real numbers. I guess the length of the input is n, right? You have n real numbers. You want to put them in the correct order. If you have like a shortest path problem, maybe the input is, well, I guess it's the digraph and the length function, which maybe you could say the size of the digraph is the number of arcs in the digraph, or something like that, okay? Or you could say it's the number of vertices, and you might be measuring in terms of that. But basically, we want that we want that the running time scales up in a sort of reasonable way when you grow the size of the input, right? So the nice thing about like for example, if you have a n to the n squared algorithm, big O n squared, the nice thing is, suppose I have some input of size n, and now I have an input which is twice as big, right? So it's 2 times n. Well, then the running time, you should expect your algorithm to run, it's only going to take 4 times as long, right? So if to run your algorithm it took a day, okay, now you've doubled the size of the input, it's going to take you 4 days, right? Which is sort of somewhat reasonable, I think. It's going to take you longer, but yeah, it shouldn't blow up too much. Whereas if you have like an exponential time algorithm, suppose you have an algorithm that runs in time 2 to the n. Now when you double the size of your input, the running time is going to square, right? Because it's going to go from 2 to the n to 2 to the 2 times n, right? 2 to the 2 times n is the square of 2 to the n, which is kind of horrific to square the number of steps every time. Okay. So yeah, whenever I say that an algorithm is efficient, I mean it's big O. So this is, we just call this polynomial time or polytime. Of course, it might not be written like this, right? Like if I had like an algorithm that ran in time big O n squared log n, right? You shouldn't say that this is not polynomial time because logarithm's not a polynomial, right? This is still polynomial time because, I mean, log n grows slower than n. So like, n squared log n in particular grows slower than, so it's little o of n cubed, right? So if you can bound it by something that's a polynomial or grows even slower than some polynomial, then that's polynomial time, right? Any questions about any of this stuff? Okay. Okay, so when we're talking about what makes problems hard and things like that, it's kind of convenient so we've been talking so far about optimization problems where you're trying to compute the maximum or minimum of something. But it's going to be convenient to work with something called decision problems, which are just yes/no questions, which are closely related to optimization problems, but it's not quite the same thing. So yeah, we're going to focus on this problem that we can't solve, basically, for most of this lecture. So yeah, let's talk about decision problems. So a decision problem is a problem that can be phrased as a yes/no, so yes or no question about some input mathematical structure. So you've got some kind of input, and you want to answer a yes or no question. This so-called input we'll often call this, so it's called an instance of the problem. So the shortest path problem is not really a decision problem, right? It's asking for the minimum length of a path. But you could like turn it into, I mean, you could find some associated, related decision problems, right? You could say, for two vertices S and T, you could ask, is it true that the shortest path has length at most 100? Right, so that's turned this optimization problem into kind of a decision problem. And then you could just keep asking that question for different lengths of shortest path, right, until you find the answer. So yeah, technically for a lot of this complexity stuff, we're going to be talking in terms of decision problems rather than optimization problems. So here's an example. Maybe before the example, I'll give you just a quick definition that probably people know. So it's the definition of a graph. So a graph is a pair, so graph G, let's say, would be E, where V is a set of vertices and E is a set of pairs of vertices. Well, I should say unordered pairs. So it's different than a digraph, right? So unordered pairs of vertices called edges. Right, and we usually, because we'll often just introduce the graph, and then we'll write, BG to be the set of vertices. And E of G is the set of edges. Okay. So yeah, it's, if you've taken 222 or 322 or any kind of introductory discrete math or graph theory course, you're probably somewhat familiar with graphs, right? It's just you take a bunch of points and you join them up. And so if I've got two vertices, U and V, with an edge between them, I would write, UV is an edge of G, just to mean that this edge is actually in the graph. Or I could write UW is not an edge, right, to mean that, U and W are not an edge, right? And so these edges are symmetric, unlike with digraphs. Okay, so here's an example of a decision problem. So for example, the three colorability problem. Which I might just abbreviate to 3col. Right, so this is, if you've seen the chromatic number of a graph, this is just asking, is the chromatic number at most 3? So the input for this problem is just a graph G. And then the question it's asking is, does there exist a function f from the vertices to the numbers 1, 2, and 3 such that adjacent vertices get different colors? So f of u is not equal to f of v for each edge u, v in the graph. Right, so this is a decision problem because it's asking a yes or no question, right? The answer is going to be yes or no for each graph. Some graphs it's going to be yes, and some graphs it's going to be no, right? So yeah, this is a decision problem. And so like an instance of this problem would be a graph, right? It's the thing you put into the input. So if you have any decision problem, if I say you've got some input and some kind of question, like the instance is, an instance of the problem is like any kind of possible input structure, right? Any questions about any of this stuff? Okay. All right, so now we're finally going to get to this question of what makes some problems harder than others. So let me first kind of tell you what the easy problems are, although easy should be in quotations because it's not always necessarily easy to solve them. But yeah, the set of the set of all decision problems that can be solved by a polynomial time algorithm is called capital P. Okay, so these are the problems that, they're tractable. So we sometimes use this word tractable. Tractable just kind of means like there is, it's kind of solvable in an efficient way. So if something is not in P, we would call it intractable. Although it's not so easy to find things that are not in P in this course. Okay, who's heard of P and NP and stuff like that? And who's like completely confident that they know what P and NP mean? Okay. Yeah, so not quite everybody. So yeah, so P is this class. A kind of strange class is NP. Okay, so and really when I talk about the difference between problems that are easy or hard, I really kind of mean what's the difference between P and NP? Okay, so a problem can be solved in what's called non-deterministic polynomial time if I'll say for every yes instance, by which I mean for every instance of the problem where the answer is yes, there is an algorithm for certifying that the answer really is yes. In polynomial time. Actually, I should say, no, I should clean this up a little bit. So there is, it's not, so okay, what I'm saying is not quite right. Okay, I need the notion of a certificate before, so I'm going to change this statement in a second. So pretend I gave this definition first, okay? So a certificate for an instance of a decision problem is an object it's some kind of a mathematical object that can be used to verify the answer to the problem for that instance. Okay, this is probably all getting very confusing, so let's maybe like step back and think of some examples. So if you think of the three colorability problem, suppose there's a graph, right? And I'm trying to convince you that this graph is a yes instance. I'm trying to convince you that it's three colorable. What's the best way, like that's my whole goal, and like you're really skeptical, and I'm trying to tell you that it really is three colorable. How would I do it? Yeah, exactly. Just produce a coloring, and then I'll give it to you, and I'll say, okay, you check yourself, right? And what would you do? And if you're really skeptical, you don't think this is going to be a three coloring, you would just go through all the edges and go, okay, they have different colors. They have different colors. You know, you would just check all the edges, right? And that checking takes polynomial time. Now, who knows how I came up with the coloring? But just the checking of the coloring takes polynomial time. You just check every edge. So for a yes instance for the three colorability problem, the most natural certificate would be a coloring, right? So what I want to say is that a problem is in NP if for every yes instance, so we're not talking about no instances, just the yes instances, like in three colorability, there is a certificate for that yes instance and an algorithm well, maybe for certifying that the certificate is, I guess, valid, I guess. I don't know, that it really is doing what it's supposed to do in polynomial time. To be honest, to me, it's an extremely strange condition. But yeah, that's what it means to be solvable in non-deterministic polynomial time. If the answer is yes, then there's a way to convince somebody that doesn't take very much time, right? I can just produce the coloring and someone can check it very quickly. The same thing is true for this shortest path problem, right? So if I say for two vertices in a digraph, is the shortest path of length at most 100? Actually, well, yeah. Right, how would I certify that? Yeah.
Shortest path, length less than 100.
Yeah, actually it doesn't even need to be shortest, because you just give any path of length less than or equal to 100, and then like maybe there's a shorter one, but you've shown it's at most 100. Yeah. So indeed, yeah. So for a yes certificate, you've got for yes instance, you have a certificate. But it says nothing about the no instances, which is a little bit strange. But now we'll let, well, maybe it's not strange. There are reasons for this. But let's let NP, so NP is the set of such problems. So the problems that can be solved in non-deterministic polynomial time. Okay. So I claim that P is a subset of NP. So I claim that anything that has a polynomial time algorithm to solve it, that problem is also non-deterministic, solvable in non-deterministic polynomial time. So it has a certificate that can be checked in polynomial time. Sorry, every yes instance has a certificate that can be checked in polynomial time. Can anyone see? There's like a slick, I mean, a kind of cheap trick to do this, but can anyone see why this is true? How would I get a certificate? Like, suppose I've got a problem that's solvable in polynomial time. Okay. What's the certificate for a yes instance? That's true. Like, part of your solving it must have, there must have been something that you.
Your proof, you just like apply it to the example. It's like this kind of.
Yeah. Yeah, I would. So I would say even like, yeah, for this, like the certificate could just be the instance of the problem from the beginning, right? Because the instance of the problem can be, you can check what the answer is in polynomial time, right? So is there a certificate and an algorithm to check it? Yeah, there is, because you could just give the original problem and say, please go check it in polynomial time. So yeah, this is true because so the certificate. Just is the instance of the problem. So it is true. So this is maybe a proof. Right, and then this is this $1 million question. $1 million American, so that's a lot in Canadian. Yeah. Is this inequality or this subset relation, is it strict, right? Which is completely absurd. Obviously, it's kind of strict, right? Like, why would it be the case that everything that can be, where a yes certificate can be checked, why would it be the case that you can actually solve the problem in polynomial time? There seems to be no good reason, but no one knows how to solve this. So, any questions about any of this stuff? Yeah?
A yes solution is just any problem you can prove can't be solved in polynomial time.
Oh, like, yeah, if you could find something here that's not here, where you can, you can definitely prove it's in NP and you can prove it's not in P, that would answer it with a yes, yeah. Yeah, this is basically the thing is we have no idea how to take something in NP and show it doesn't have a polynomial time algorithm. It's hard to show things don't exist, right? Okay. Any other questions about that? Okay, remember I kind of like mentioned there's this kind of weird asymmetry here that we're only talking about yes instances. It turns out there's another class of problems where you just talk about no instances. So like, so co-NP is what we call this class. So this is the set of problems. I should say decision problems again, not like optimization problems or anything like that. So yes or no questions, such that every no instance has a certificate that can be checked in polynomial time. So generally speaking, if I have a problem that's in NP and I want to have a problem in co-NP, it's kind of easy to just say, okay, I mean, for example, three-colorability. The question, is the graph three-colorable, or does the three-coloring exist? That's in NP. If I just say, is it true that the graph is not three-colorable? That's going to be in co-NP, right? Because if it's not three-colorable, then it has a three-coloring. But there are some questions that sort of more naturally live in this class. So one example is the problem, prime. So here the input is a positive integer. Let's say in binary, so written in binary with n bits. I mean, or you could say it's got n digits and it's written in base 10. It doesn't really matter. And the problem is this number, is it prime? Right, so I claim that this very naturally lives in this set co-NP. Any kind of argument why? Like, what would be the certificate? Yeah.
If it's false, prime factor, and that's the division's polynomial.
Yeah, exactly. So yeah, so it's so for no instance, yeah, the certificate. Well, a natural certificate anyway. There could be other certificates, right? So I'll just say a certificate for no is, yeah, well, yeah, a factor. I mean, you could say a prime factor, or you just anything that divides that number, other than it and 1, right? So here's another kind of maybe sibling of the p equals co-NP, or sorry, p equals NP problem. There's also some kind of maybe belief that, is it true that p is just the same thing as NP intersect co-NP? So I mean, actually, maybe I should also say P is definitely a subset of co-NP, right? Because for the same reason we said over there for NP, the instance could just be, or the certificate could just be the whole instance, right? Because you can solve the whole thing in polynomial time. So that gives you proof that it's a no instance, just the instance itself. So indeed, P is a subset of this, P is a subset of this. Maybe it's just the intersection of the two. But this is, yeah, also an unknown, unsolved problem. Not sure if they give you $1 million for this, but you'd definitely be famous. So this actually kind of brings me to something called duality, which is going to be an important topic in this course. But first, are there any questions about any of this philosophical stuff? Okay. Yeah.
So NP and P, those are sets of like every single decision problem.
I guess so. I mean, I'm being a bit kind of vague on that. There's probably some proper definition, but I don't really want to be super like if you see something that you think is a problem, then it's like a decision problem. It's a yes or no question. Yeah, then I would say it's yeah. Well, oh, sorry. Oh, yeah. Maybe I was misunderstanding your question. Are these all of the top possible problems? Was your question, right? So. Oh, yes, sorry. So there are things that are not in P, not in NP, not in co-NP. Like there are problems beyond this whole thing. So there are many classes of problems. That we're not going to really talk about. So like there's a problem called P space, or a class of problems called P space, right? Which it's the set of problems that you can solve using a polynomial amount of space, like bits on a computer or something, in as long as you want, right? So it doesn't care about time, it just cares about space. You could have like exp time, right? Which is problems that can be solved in exponential time. You have like log time. You have log space. You have all of these different classes of problems, and these are all kind of interesting, but we're not going to talk about them. So there are things that live in these families, but might not be in P or NP. But yeah, I don't know if either of these things answer your question or not, but
Both do, actually, yeah.
okay, great. Any other questions? Yeah, so we're going to mostly focus on P, NP, and co-NP. Other things exist. So this is also going to be a bit theoretical and philosophical. Eventually, we're going to actually analyze some real algorithms, but yeah, I just sort of want to give you these kind of insights first. So for an optimization problem, right? So we're maximizing some function. So let's say I let m be the maximum of some function f of x, such that x is in x, capital X. So yeah, these are the types of things we want to compute in this course. Now, there's a bit of asymmetry, I mean, kind of related to P and co-NP, that, suppose I want to show that this capital M is at least 100. So like, what's the most natural thing you would do? Yeah. I hope I'm not like insulting your intelligence with these questions. I mean, it is that easy, right? You just want to find, so what you would do is find x such that f of x is at least 100. I mean, in some sense, I mean, this x, really, this is a certificate, right? Right? It certifies that the maximum is at least 100. And if this function f can be computed like, in polynomial time for any given x, then this is maybe a good certificate, like it's a polynomial time checkable certificate. But here's the thing, to prove, I mean, what if I wanted to prove that m is at most 100? Like that seems like that problem sucks, right? If I want to show that it's at most 100, no matter what I've checked, if I've gone through many values of x, there could still be one where the answer is larger than 100. So this becomes much harder, right? I mean, it's seemingly harder. I mean, this also comes back to this earlier question about P and NP, it's hard to show that things don't exist, right? So what I want to show here is there doesn't exist an X with a value larger than 100. So this idea of duality, though, is this magical, extremely powerful idea in optimization, where actually you take this second problem, which seems kind of impossible. You need to check everything. And you actually transform it into, in some non-trivial way, into another problem where it's actually a minimization problem, and then you can just find a certificate. Okay, so this is going to come up all over throughout the course. So the idea of duality is that many optimization problems have, well, duals, meaning that there exists a function, a set y, and function, let's say g, from y to the reals, such that if I take this maximum that I'm trying to compute, so the maximum of x such that subject to x being in x, okay, for some specific reasons related to the problem itself, I can actually bound this kind of like theoretically by the minimum of g of y subject to y and y. Okay. So like what you sort of want to do is you take some problem, right? And you want to formally prove that there's some other problem that kind of limits that problem, right? The maximum of this one can't be larger than the minimum of this problem. And if you can do that, that gives you an approach for proving an inequality like m at most 100. Because what I do is, suppose I can find this g and this y in polynomial time. I take my f and my x, I convert it into the g and the y, and then I just find a certificate over here, right? If I can find some y where g of y is at most 100, then I win, right? So this kind of relationship, so of course, here I've got a less than or equal to, which means that sometimes maybe you might want to prove this, but you can't actually do it with this function, because maybe there's a gap here. So this kind of relationship where you have a maximum bounded above by a minimum, this is called weak duality. Okay, which can be very valuable in cases where, I mean, sometimes the bound that you want can actually be proved by finding a certificate for this problem, right? And then that makes things simpler. But sometimes you have this like amazing thing that actually equality holds. So when equality holds, it's called strong duality. And when that happens, it's kind of an amazing thing because it means that, I mean, it's kind of like, it's very much related to this P and co-MP thing, right? To prove this, to prove this lower bound, I want to find a certificate in my original problem that certifies it. I could take, and to prove the opposite inequality, if you have equality here, to prove the m is at most 100, I just convert it into the dual and I find a certificate over there, which is kind of like related to being in P and co-MP. Okay, any questions about any of this? This is again like we're like up in the sky, like looking at general problems. Let's actually come up with a concrete example to hopefully make this make sense. We need a couple of definitions. So a graph is bipartite if, well, let's say the graph is called G. The graph G is bipartite if there exists a partition of the vertex set V of G into X and Y such that every edge has one endpoint in each of X and Y. Okay, and I want to also define a matching in a graph. So a matching in a graph G is a set M, which is a subset of the edges of G, such that each vertex is in at most one of the edges in M. So each vertex is contained in at most one edge of M. Okay, so bipartite graph is just a graph with two sets X and Y, where every edge goes from one set to the other set. Right, so that's the first definition. And then a matching is a set of edges such that, so for example, these two edges would be a matching because they don't have any common vertex. So like these two edges are not a matching because they hit the same vertex twice. So this would, so matching in a bipartite graph. Okay. So yeah, a natural problem is, where I've got like a, problem where I've got an input, which is a bipartite graph. And then the problem is, so it's called G. G is the graph. Find the cardinality of the biggest matching. So I'm going to introduce some notation. So I'm going to denote this by nu of G. So nu, it's a Greek letter, it looks like a V kind of. And that's the maximum cardinality of M such that M is a matching in G. Right, so this is an optimization problem, right? we are trying to optimize some function. Yeah. You could think of it as optimizing some function over subsets of the edges or something like that. We're trying to find the biggest matching. So I'm trying to like illustrate this idea of duality. So here's the thing. So, okay, if I wanted to show that nu of g is at least 100, I would just produce a matching of size 100, right? And then I just check it's a matching, done. So, so certifying that, let's say nu of g is at least some number, like 100. I mean, that's kind of, it's fairly easy, right? If you know how to find the matching, right? So it can be done by just producing a matching. But proving like an opposite inequality, that the matching number is at most something, that's like not obvious. Like, how would I do that? And this is where this duality thing kicks in. So I'm going to make a definition. So vertex cover is a set of vertices in a graph such that every edge has an endpoint in S. Okay. And let's say tau of g is the size of the minimum size of a vertex cover. Okay. So my original problem was computing a maximum. Now I'm computing a minimum. And I claim that there's some kind of a duality thing that's happening here. So let's prove like a weak duality statement. So for any graph, and let's not even care, I'm not even going to care about bipartite for this. So for any graph G, I claim that nu of G is at most tau of G. Okay. Can anyone see why? I'm throwing a lot of definitions at you all at once, so it's maybe not completely, maybe you're still digesting them, but
It's like the number of edges, like maximum matching in some sense. Or basically we don't want to pick two vertices that correspond to the same edge because it's like minimum. So just one, so it corresponds to just the first one. Like there is a correspondence between like
it's in some sense what you're saying is going to be true for bipartite graphs. It's not actually even true for all graphs though. So this is not going to be equals always. So to get this inequality, it's just like a pigeonhole kind of thing. So I take my graph, right? And take any vertex cover S. So let's say it's got like 5 vertices or something. And I might as well take the minimum one, but this is going to work for any vertex cover. So suppose this vertex cover has 5 vertices. Could I have a matching of size 6? And remember what a vertex cover means. Every edge in the whole graph has an endpoint in S. But edges in a matching aren't allowed to share endpoints. So suppose I had a matching of size 6, right? For the first edge, I could say, okay, well, maybe the first edge in my matching touches this one, maybe the second one touches that one, but they're not supposed to hit the same vertex, right? So you couldn't possibly have a matching of size 6 because every edge in the whole graph hits one of these vertices. So, so for any vertex cover, so yeah, if you had a larger matching, by pigeonhole, 2 of those matching edges would hit the same vertex. That would be a contradiction because it's a matching. So yeah, so any matching M and vertex cover satisfies the size of M is at most the size of S because it's by pigeonhole. Okay, so I want to think of you to think of this, like, kind of think of this in your heads in this, like, framework of duality, right? I have a maximization problem, I have a minimization problem, and basically the minimization problem gives me some kind of a bound on my maximization problem, okay? Yeah, and for all graphs, the relationship is like this. It's an inequality, but then there's this kind of amazing theorem called Koenig's theorem, which says that if G is bipartite, then nu of G equals tau of G. Okay. So this I could think of as like a sort of weak duality. And this I could think of as like a strong duality. Like we said, to certify that the matching number is large, I just find a big matching. To certify that nu of G is at most 100, you just need, well, in general, I guess, you could do this by finding a vertex cover of size 100. And if it's bipartite, then actually this is basically equivalent to having a vertex cover of size at most 100. Okay. Any questions about that? Okay. Yeah.
Just because you find like one of these dualities, does it mean that the one that you're like, the second one is easier? Like it doesn't necessarily mean that, right?
Doesn't necessarily mean that. Well, when you say the second one, you mean like the kind of dual problem or something?
It could be harder than the original problem when you started.
It totally could, and actually this is a good example of that. So, okay, if you have like an equality, then I guess they're the same difficulty, they're just the same thing. When you have an inequality, actually in graphs in general, to compute the matching number is polynomial. To compute the vertex cover number is NP complete. Or which is a concept we'll talk about later, but basically like this problem is hard in a general graph, but this one is polynomial. So yeah, indeed, sometimes you can find some kind of a dual problem where the complexities are actually different. In the case where you have an inequality, if it's an equality, of course, they're exactly the same thing. So yeah, any other questions about that or anything? Okay, so we're going to see a lot of examples of basically some sorts of kind of weak and strong duality theorems. Maybe I'll just save that for when we come to them. And yeah, we can. I'll see you guys on Thursday. So.